Big data is cursed. You can find almost any pattern in a sufficiently large and complex data set. So what have we seen so far? We've seen that big data is very large. We say that's high volume. It's got a lot of variety, and that tends to mean that every big data problem is unique. We call that high variety. You might say, well, let's just avoid big data altogether. But big data has a huge upside. It's very useful, tends to be very robust, and the high variety means almost anything can be considered data. And nowadays, almost anything is. But there's a downside. Big data is also high velocity. It can occur so quickly or require algorithms that run so slowly, results are produced too slowly to be useful. Let's look at an example, in particular the subset sum problem. Here we have a subset that adds to 0. Here we have another subset that adds to 0. And the question is, what's the largest subset that adds to 0? If we just had 250 integers, we would have 2 to the 250 subsets to check. And on the Titan computer in Oak Ridge, that would mean 10 to the 51st years, just for 250 integers. Also, big data is cursed. In a very high dimensional space, nearest neighbors can be very, 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 very far away. And we may have information that we extract that's not useful. Let's look at the curse of dimensionality. In very high dimensional spaces, points tend to be very far apart from each other. And averages tend to drown out useful information. For example, the ones and zeros. So if we have factors, x sub j, that are either true 1 or false 0, then here are all the possible combinations of ones and zeros in 2 dimensions, and here they are in 3 dimensions. If two observations differ only in one factor, we'll say they're adjacent. We'll say that the diameter of these structures, which show adjacencies, the square in 2 dimensions and the cube in 3 dimensions, is the maximum number of steps that it takes to go from one vertex to another. In 2 dimensions, the diameter is 2, and in 3 dimensions, it's 3. The generalization of this is called the hypercube. In n dimensions, the diameter is n. What does that mean? That means that vertices on the hypercube can be extremely far apart if n is very large. So a set of big data can be spread across enormous distances, even if each individual factor has a very small range. This is the curse of dimensionality. There's another curse, which we call the curse of phantom information. A lot of times we think of big data as random, so we can apply probability theory. In particular, random-like patterns may be the answer we're looking for, or they may be misleading, or they may simply be there. The key here is that in a sufficiently large and complex data set, all 3 of these are possible. So how do we model a random process? Well, we have a sample space, and the sample space of all possible outcomes is inside the universe of everything. Subsets of the sample space are called events, and the probability that A occurs is denoted with probability of A. Things outside of the sample space but inside the universe are said to have probability 0. So let's apply this to modeling a coin toss. So our sample space is heads, tails. Our event is just heads. We are going to conduct n trials, n independent tosses of the coin. For each trial, we'll have an xi which is 0 if tails and 1 if heads. The probability is simply the average over these factors as n goes to infinity. In particular, the sum of all x's is the number of heads. The probability is as n goes to infinity. Now let's look at this in a simulation. So here we have, for probability a half, we're flipping the coin, and you can see in the box in the upper right, we have black if it's a heads and white if it's a tails. And notice how this grows toward the expected probability of a half. So what we're looking at here is we have the relative frequency, which is the head count over the number of trials, and sure enough, it approaches a half. Notice that the simulations are for 50,000 trials. Let's suppose we have a probability of 0.25. Once again, we're counting the number of heads, dividing by the number of trials, and the horizontal axis is the number of trials. And we can see that we're quickly approaching 0.25. So we're getting heads about a quarter of the time. And if you look at the box in the upper right, the area of black is about a quarter of the white. Now, suppose the probability of heads is 0.05. It's going to take a long time, or we wouldn't be surprised if it takes a long time, before we get the first head. Once we do, however, the process kicks in and we see that it converges again. The important thing in all of these simulations is that all of these simulations we reached the probability after only about 10,000 trials. What we are seeing is an example of what's known as the law of large numbers. As the number of independent trials of a process increases, then averages over measures of the trial data approach what you would expect theoretically. And in particular, relative frequencies approach a theoretical probability. Notice this tends to happen after only a few thousand trials. Many independent trials means many independent variables, which means many patterns. So suppose we have 20 consecutive tosses where there's tails and 18 heads and then a tails. This almost certainly will not happen in 100 tosses of a fair coin. It almost certainly does happen, however, in 1,000,000 coin tosses. So what if we were to say that this run of 20 tosses predicted whether or not we had a fair coin? Well, it would be wrong. So the larger the data, the more the patterns occur, and big data is billions or trillions, megabytes, petabytes. So what about events with probability 0? Well, they actually do happen in big data sets. Let's look at an example. A coin toss ends balanced on edge, no more than one time in 1,000 tosses. If we toss the coin 1,000 times, we might be surprised even if the coin balanced on its edge. In 4,000 tosses, probably no more than 2, and 9,000 tosses, no more than 3. And this little simple model of when a coin balances on its edge, in 1,000 n-squared tosses, we expect to balance on edge no more than 10 times. If this is the case, then the probability of balancing on edge is 0, as we would have expected. Now, where this comes into play with big data is that we often have missing data. So here we actually have some real-world data where NA marks where a coin balanced on its edge. Even though the probability of balancing on edge is 0, we haven't ruled out the possibility of seeing as many as 100 balancing on edge outcomes in these 1,000 observations of 10,000 trials. That means that up to 10% of the observations could contain trials where there is not available NA data, even though the probability of NA is 0. So when we're working with big data, we should expect high volume and high variety. Our goal is usually to find small collections of informative patterns with a huge amount of non-informative, random-like data. And big data is so large that probability 0 NA events do often occur. So what is big data? We tend to think of it in terms of the 3 V's: high volume, high variety, high velocity. And we tend to think of big data as useful and as productive as it has become. It's also cursed. information may be difficult to obtain, and the information we obtain may not be meaningful.